Okay. Right, so the statement of the polar decomposition, or you can do it the other way too. So it's like if here it means that V is a unitary operator and Q is a positive operator. But in general, U doesn't have to be the same as V, and P doesn't have to be the same as Q. And in general, you can do what's called the singular value decomposition. It's usually written like this, like on Wikipedia. And an informal statement of the singular value composition, you can think of it as every matrix can be diagonalized, but in two bases, not just one. And this U and V are the change of basis from the standard basis to the left and right singular value vectors. Here in Dirac notation, let's see. So this E and F form two different orthonormal bases. And then, well, I don't remember which symbol we used for the singular value last time. Probably some, yeah, it's either square root of P or P. Yeah. But this is to signify that this is, well, is a positive number. So sometimes people write something like delta square or something. But here, yeah, it's not so important. Just I just wrote this to be consistent with last time. All right, and by the way, yeah, here is how you can write SVD in the Dirac notation. It's kind of trivial for the normal operator. So for normal operator, since you can diagonalize them, right? So it's really, it means that there's a eigenbasis that form a complete orthonormal set, and then you put some eigenvalues in here. Which for an arbitrary, a general normal operator, the AJ doesn't have to be real. It can be any complex numbers. All right. So, and then feel free to ask any question if you have about the stuff. But today I want to talk about the axioms of quantum mechanics. And this is obviously something that you guys have seen before. The point is that we're gonna write this down, and then throughout the course, we will modify and in fact generalize all of them. Right. Well, first, okay, you may have heard, right, that quantum states correspond to normalized vector or something, right, like that. But here we're gonna be a bit more fancy. Quantum states are rays in a complex Hilbert space. And what I mean by ray is that a ray is an equivalent class of vector where we take two vectors to be the same if they only differ by a multiplication of a complex number. So this C can be anything that is not 0. So by this symbol, I just mean it's like a subtraction for sets. uh, why is this true? Well, for you can multiply a quantum state by any complex number, not just phase, right? So here for rays, I define equivalent class up to an arbitrary non-zero complex number. Where usually, like in quantum mechanics, you just say that, oh, you can multiply it by a phase, right? But yeah, actually, unless you're computing probabilities, it doesn't matter what the scalar multiplication, the scalar factor in front of the state is. And you can keep like doing computation, and then at the end, when you want to compute the like probability from measurements, then you can normalize it. That's fine. So usually, yeah, we normalize z to be something that has magnitude 1. And I would say that such normalized vectors or normalized ket are what we call state vectors. Yeah, and actually in numerics, sometimes this is nice. The fact that we don't really have to normalize it through our like time evolution or measurement, for example, until you want to compute the probabilities, because the act of normalization or like renormalization is non-linear. And so sometimes you kind of just want to write program where everything is linear, and then you just normalize everything at the end. And then once you do this, you still have the freedom, the phase freedom of this complex number left, right? And then this is usually called a global phase, and it is unphysical because no measurement can reveal global phase, essentially. And that is based on the way that we compute probabilities in quantum mechanics, right? Which I'm gonna write down in a minute, but you probably already recall that when you compute probabilities, everything is kind of like the absolute value of the inner product or the absolute value square. So unphysical. And just a remark, in contrast to global phase, sometimes people talk about the fact that relative phase are physical and important. Right? So for example, if I write, let's see, if I write a quantum state as the quantum state as a linear combination of like two vectors or two other states, but here I'm not normalizing it. But okay. Yeah. The phase here would be important, right? Because if I change the phase here, I change the physical state, the overall state. And we'll see this clearly, like geometrically, pictorially for the case of qubit today. So just a little comment that in textbooks, when people in quantum mechanics 101, sometimes people usually start talking about global phase when they talk about something like geometric phase or Berry phase. Then at first they'll say, oh, it's unphysical, it's unobservable. But then here is how we observe Berry phase, for example. And actually what they all do is just turn a global phase to a relative phase by imparting a phase only on one subspace. And this can be done, for example, by interferometer. Like if say I have a double slit, right, and have a source, and then I these two holes split the wave function of the source into two, and so state here is like a partial wave function, and then I have like another partial wave function, and then if you can modify the phase on just one of the part, and then after that you can observe the phase from the interference of the two when the two partial wave superposed. Right? Yeah. So okay. Important global phase is always unphysical, and so you might think, well, can we get rid of the global phase? And the easy way to do that is that you can, instead of writing down a kit for the state, you can write down the projector instead. So the outer product of the kit. And this will eliminate the global phase, right? Global phase. Because whatever phase that you have here, you have a complex conjugate of it here that they cancel, right? And this will become a way to move forward later when we want to modify the axioms for the state, when we move to talking about density operators instead. Right. So then measurement. Okay, maybe I should kind of make it make the statement parallel in the sense that I can talk about a quantum state here and talk about a measurement here. But anyway, measurements is the way that we have been taught, which include the general case when you have degeneracies in your measurements. It's a set of orthogonal projectors. And this is a set of projectors such that this is true. So when Js equals K, then this reduces to the definition of the projector. Of course, I have to have all of them are Hermitian as well. And when J is not equal to K, it just means that this is the meaning of orthogonal. That sum to 1, so sum to the identity. And when measurement happens, we have two rules, right? One to calculate the probabilities, and another to calculate the post measurement state. Calculate the probability, and this is called the Born rule, which famously Born got it wrong the first time. The probability of getting the J's outcome uh, is the trace of the projector corresponding to the J outcome and the state. Uh, I just call small pj. And the post measurement state is just, we'll just you just use the projector in the way it's intended to be used, right? You just project it onto the subspace corresponding to the outcome. So you just apply the projector to the state before the measurement, but then this is not normalized. To normalize, you have to divide it by the square root of the probabilities. And this way of introducing the measurement is, I hope, consistent with sort of the philosophy that I espoused before, that you don't really need observable anywhere. But of course, if you want to define an observable, then this would be the sum of the projector weighted by whatever you assign as the label of the outcome. Which are arbitrary, right? Some textbook, for example, would argue that the physical observable has to be Hermitian because of sort of like philosophical motivation, that because the value of the outcomes are real numbers, something like, oh, we can measure real numbers but not complex number, right? But well, if you just want orthogonal projector or like eigenstates that form a complete orthonormal set, you can use any normal operator. And then for any normal operator, you can, and I think we discussed this last time, I can break this up into the real and imaginary part, where both of these permission. For example, this would just be something like this, right? This permission. So it's kind of like if you add and subtract a dagger, then you can do it. You get this decomposition. Oh, and this can be done for any arbitrary linear operator. It doesn't have to be normal. But when it's normal, the real and imaginary part would commute, which implies that then you can diagonalize both parts at the same time. They have the same eigenvectors. And so then if you can do that, if you do that, then I can, if this is normal, right? I will have like an eigenvector here, and then sort of real part of the eigenvector of this guy, and then the imaginary part in the same eigenbasis. And so you could imagine measuring a complex physical quantity by measuring its real part and imaginary part separately, because they commute if the operators are normal. And so I would argue that this is really sort of an artificial label that we put on the outcomes. The only important thing, right, is that if you give the same label to orthogonal state, then you must really mean that you cannot distinguish those outcomes. That's the only, I would say, something that would correspond to physical or operational operational act of measurements. Yep. And this projector P, you just lumping the eigenvectors with the same eigenvalues together. What was I gonna say next? So maybe I should say this outright, that this is called the projection postulate. Well, I'm not sure, but definitely it's an assumption of repeatable measurement. And you can find this in like Dirac's book, for example. And this is the assumption that I think you might have heard, right? That we assume that if I make a measurement once, then it's if I make a measurement once and then I keep making making a second measurement without the time passing, like approximately. So the state hasn't changed yet. This postulate say that you should get the same measurement always, like 100%. And the only way that that happens is that the state is basically the state that you, the measurement project you onto the state correspond to the outcome that you have, right? But yeah, we'll see later this, or you can imagine that physically this is not always true. Right? It's an assumption that ultimately would have to be tested in the experiment. For example, if I have like a lattice of atoms and then I shine some light to measure where some of the atoms are, maybe it will be hit by the light and then it's got fly off from the traps. Or if I have a photon counter that detect the photons when the photon come in, usually it would absorb the photon and then destroy the photon in the process. So in those cases, clearly this projection postulate does not hold. Right. Yeah, I feel like I have something more, but I forget for now. So let's move forward. And then you have the dynamics, right? And the third, and I think the final part of the axiom is that the time evolution of the state is unitary. So for example, state at time t1 plus t2 can be obtained from the state at time t1 by applying the unitary that will correspond to, maybe to be more precise, I should say that it corresponds to a period of time, right? T2, T1. And this is to say that I have T1, T2. So if I march forward in time, the axiom is that this U is unitary. When in fact it's it's the same as evolving backward in time. Minus T2. Or whatever the you know, the negative of the argument here, right? So this come from essentially this postulate, you can think of it as coming from the measurement postulate, because Wigner proved the theorems that if there is a map, okay, it's map M that preserve the absolute value of an inner product. So I can just write the symbol. Yeah, so for simplicity, I just define this. So if you have a map that preserves this, doesn't even have to be linear in the assumption, but Wigner was able to prove that it is either then and we want something like this, right? Because in our theory, the inner product has the meaning of probability. So like the norm is like the probabilities, inner product is kind of like the transition probabilities. But at least this is we want, if we want to keep the state normalized under time evolution, then this map is either unitary or anti-unitary. And really this means that it's an anti-linear and unitary map. An anti-linear map. So have you heard of the anti-linear map before? So this is not even a linear operator actually, because it's anti-commute with I, basically, so with the imaginary unit I. For example, if I have a complex conjugate map is an example of this kind of maps. So if I, and you remember, right, that we discussed that to define complex conjugation map, you have to define it in a particular basis, because it depends on the basis. So if I define something like this, if I define a complex conjugation map in this basis, and then this is some complex number, uh, when I act, it's still linear in the sense that I can distribute this into the sum. But when it moves past a complex number, then it's apply complex conjugation. Yes. And it turns out that any anti-linear map is a product of complex conjugation and then some linear map. And then unitary here just means that it has this property, right? And well, what's the problem with this kind of maps? Why can't we use it to evolve our quantum states? You might have seen this if you learn about discrete symmetry before, like time reversal. Yeah. But yeah, we didn't teach it in the first semester of quantum here. There's just no time. Well, technically, it's called time reversal, but it's really just momentum reversal. But yeah, it's another topic. It's a whole chapter on discrete symmetry, like charge conjugation. You see something like this in like quantum field theory. But the problem with it is that it doesn't have the group property. For example, here, if I want to evolve, so let's say I want to evolve this state from time 0 to t1 and then t2, then I can apply unitary operator in series, right, in sequence. And then t2, t1 would be, so here if I start from 0, right, this would be the same as evolving by the combined duration of time. However, okay, I think this is the way that we argue it. So conversely, if I have a unitary operations that maps you from some time to some later time, then I sort of can always break down the time step, right? And then write it as, for example, the square root of itself. However, something like complex conjugation here, which is a discrete map, you cannot really take a square root of it, because like what's the square root of taking a complex conjugate? Yeah, so that's why they're unphysical, but sometimes they are useful maps to consider in both in quantum mechanics, like traditionally, and quantum information theory. But it's kind of like a discrete time. Well, it's not really a time evolution. It's a discrete step. This map that you apply in discrete steps. For example, some things like complex conjugation or partial transpose can be, this kind of map can be applied to measure entanglement, for example. All right. Okay. Any question up to now? Because we are already finished the axioms of quantum mechanics. The big C? Yes, big C, lotat. Yeah, it's a map. Here is a complex conjugation map. Yeah, but why can't you define it? Have you heard of Grassman number? Grassman numbers, like a number that anti-commute. Yeah, in that case, is the name is really misleading because if it doesn't commute with number, then it's not a number, right? Uh, but here it's fine, right? Because I'm just saying it's some operator. I'm not uh, I'm not even saying it's linear because it's not. It's called anti-linear because of this. Yeah. But you can think of it as, I mean, an operator is just some map, right? You can think of like just defining a map by giving it, right? And if you're not worrying that it has some property that I mean, when we talk about something like linear maps, then we have in mind that we have some restriction on how it acts, right? How we can assign the rules for the map. But if not, if you say it can be anything, then you just define it to be what it is, right? Yeah. All right. Yeah, and as I said, we will modify this as we go. So maybe I want to write it. I have a little corner that kind of summarize these axioms. Axiom summarize. Or a bit informal here. For example, the states are raised. Yeah. Measurements are sets of projectors. Or I can say measurement outcome correspond to a projection operators. And time evolutions are unitary operators. I just write as unitaries to be the noun. That a unitary is well, I guess people don't say a unitary to mean a unitary operator, but people do say unitaries when they say like, oh, it can be some unitary operators. So here we are using unitary as noun, and this is not in a dictionary or anywhere, but we use it anyway. And we will generalize this. So states will become positive operators. Projector will also be positive operator. Unitaries become completely positive map. But we are not going to do it today. We are not going to do it in one go. Just do it like uh, when it comes up. Okay. So the best test bed or playground that you can play around with these rules are when you have a two-level system, right? Also known as qubits. And this physically means that you have two states that are perfectly distinguishable, which will be designated as 0 and 1. And by completely distinguishable, I mean that in quantum theory, this corresponds to them being orthonormal. Right? And so we can use them as a basis. But of course, we know that in a two-level system, in this Hilbert space, we have a lot more states. We have infinitely more states. But in general, they are not perfectly distinguishable, right? Because their inner product is not 0. And so you can always, there's always a chance that you can mistake some state for a state that is not orthogonal. Right? So physically, this has, there are many examples, right? Can you think of, I mean, it can be just, yeah, it doesn't have to be clever or anything. It's just, yeah, like spin 1/2. Right? Polarization of light, right? That's vertical and horizontal, except that I guess optics people usually use as a basis right and left circular polarization instead. Or something like related to what you learn when you like solve your equations in quantum 101, like you can have double wells and then take the ground state of two wells. So I guess there has to be this is kind of like approximately qubit, because you can state here can still tunnel here. Right? So by ground state, yeah, I mean something like this. But as long as the wall is like kind of tall enough or wide enough, then this is like approximately a qubit. If you can keep them in the ground state. Experimentally or like in real world is no no system is really a qubit, right? Well, maybe if you have like a fundamental spin 1/2 particles, but usually we have access to a lot bigger Hilbert space, right? So for example, you have if you have a spin, right. So like if you have usually in when we first learn about atomic physics, we would just talk about just talk about the spin or the internal state of the electron, right, and like energy level and whatever. But and we in the simplest sort of analysis, we just treat the nucleus as something that's unmovable and doesn't have internal structure, right? But in reality, electrons also interact with this nuclear, like spin degrees of freedom of protons in nucleus. So in general, you usually never have a qubit. You just have a lot, Hilbert space is much bigger. But if you can restrict, practically like restrict yourself to a two-dimensional subspace, then you can use this as a qubit too. And by restricting, so for example, here I give a counter example. So you may think that, for example, if I have a harmonic oscillator, right, then maybe I can think of maybe the ground state and the first excited state to be the qubit. except that if say, if you want to, your lab want to experimentally use this as a qubit, and now how would you transition between the two states? Then you just fire some laser with the frequency that match the energy difference here, right? But the problem is that, say, if I want to, so let's put this 0 and 1, so ground state and first excited state. So suppose I want to kick the zeros, the ground state to the first excited state. I would just like fire laser, and then the state here jump to here, right? But the problem is that the energy difference are uniform. So if your state has some population that's already in the one state, it would get kicked out of this two-dimensional subspace. And so, for example, experimentalists would use, well, they would not use harmonic oscillator as a qubit, but they would use an harmonic oscillator, or sometimes they call like the nonlinear oscillator or whatever. So sometimes they like add some kind of asymmetry here to make the like spacing difference between two levels, and then they choose whatever two levels that, you know, they have a laser that they can buy. Yeah. In the end, the ultimately what restrict your experimental capability is just money. Yeah. So, how do we describe this mathematically? Well, at first glance, there's not much to do. So any superposition like this, where the sum of squares one is a valid quantum state or a state vector. But yeah, we can do something more in the case of qubit. And actually, this is a unique thing that you cannot do in higher dimension, is to draw this in 3 dimensions. Well, how to do that? Well, at first is so without constraint, this would require 4 real dimension. Right? Each complex number has 2 real numbers, but in fact you can eliminate 2 of them, because as we say, the states are just rays, and so you can eliminate 2 degrees of freedom corresponding to, you know, the arbitrary complex number that you multiply. So one is normalizations, and another is a global phase. So you can do it like you can do a polar decomposition of, or write the complex number in a polar form. Okay. But yeah, R1 and R2 are real and positive, and then phi 1 and phi 2 can be anything from 0 to 2 pi. Now I can pull out the global phase. So suppose that I pull this out. Then the phase here would be phi 2 minus phi 1, right? So we sort of just ignore this. And then if we redefine these new variables and then take into account this constraint, I can write it like this. And there will be a reason for 1/2 in a minute. Well, depends on where theta and phi are angle are really spherical coordinates angle. So theta is from 0 to pi, and this is from 0 to 2 pi. And the picture that emerges is the following. Right. Which doesn't, yeah, more like an egg instead of a sphere. Where, okay, so here I just, so this theta and phi defines the azimuthal angle and the polar angle in the spherical coordinates. So so where theta goes from the North Pole to here, then the angle that the shadow of this on the XY plane with the X axis, right? So this X, Y, Z. So according to this, we map the states 0 to the North Pole and 1 to the South Pole. And then, for example, if you have, if phi is 0, if the polar angle is 0, and then you rotate down by 90 degrees of theta, you will get an equal superposition of 0 and 1, right? Because you get cosine of pi over 4 and sine of pi over 4. And in general, everything on the equatorial plane is uniform superposition, but with a relative phase. So why do we have this 1/2 here? So what if we don't have, if I just have cosine theta and sine theta, what would happen? Well, since theta grows from 0 to pi, right? What is the cosine of pi? -1. Cosine of pi. Yeah. So under that parameterization, when I rotate by pi, I will just get the negative of the 0 ket instead, but we know that it's silly, right? Because the global phase is unphysical, and the negative of the ket 0 should be the same as the 0, as ket 0. And so we have this 1/2 so that we sort of double the angle that you need to rotate to the same thing. And it matched. So in that case, if I rotate by 2 pi, then I return to the same state, but with a global phase, but that's okay. Is that economical, this representation? No global phase. And by the way, this, of course, is called the block sphere picture. In the context of spin, but actually when this is used to represent polarization state, which is you already have in classical optics. This is called a Poincare sphere. Yeah. So yeah, something like this you can entirely see in classical electromagnetics theory as well. Okay, what's next? Right, that's the global phase. Okay. Okay, so obviously now I can write any state vector for qubit in terms of the angle theta and phi, right? Okay, so that's for states. But what's spatial? Okay, so the block sphere picture is already spatial because you cannot do that for higher dimensional Hilbert space. But another thing that's spatial for the qubit case is that the space of linear operators is also like very easy to analyze, to investigate. Basically, everything can be done explicitly, like diagonalization, finding eigenvector, eigenvalues, for example. Whereas explicitly in the sense that you don't really need to use those general formula like determinant of A minus lambda I. We can do it all by hand. So qubit operator space. And actually, I want to start by writing this, let's say, projector onto the subspace in the direction determined by the unit vector n. Just to make sure this is XYZ, right? XYZ coordinates where, so this is the hat here really mean unit vector. And okay. And in terms of spherical coordinates, this is how it works, right? Psi phi, psi phi. Well, so what is this guy? We can compute it explicitly, right? Just taking the outer product. So this is the square of this plus psi square of this, right? And then you have the cross term. Oh, let's see. Cosine times psi, and then you have the phase. Right. So this guy, if I recall correctly, this is just 1 plus cosine theta over 2, 1 minus. And I think this is 1/2 psi theta. Yeah, I think that's right. And notice that now all the angles are just theta. Right? It's like the double angle formula. Right. And so I can combine this part, this constant part to get this term. Oh, there's 1/2 too, right? And then plus 1/2 cosine theta of the difference. And then now just to change things slightly, then I can write these exponential as a sum and difference of cosine and sine, right? And this should give us, so there's sine theta in front for both of them. Right. Cosine phi of the sum, right, and then probably minus I psi phi. Right, of the difference, so this is cosine minus I hope that's right. And here it just mean that I don't mean a matrix, right? It just means that there's not enough space, so I just start here. And so there we have it, that this projector is nothing but linear combination of the identity operator and the Pauli x, y, and z. So in particular, I have x, y plus z, where these are the coordinates here, right, of the vector in 3 dimensions. And usually this is written as a shorthand by writing it as a dot product of a unit vector and the vector of Pauli matrix, which of course here I just mean that this is sort of just a formal notation, right? That you think of this as a column vector of operators. And the dot product is just a shorthand for this sum. But well, at the end, it turns out that it's not only just a convenient shorthand, because this vector actually transform like a 3-dimensional vectors. It's sort of the topic of like vector operator, tensor operators in quantum mechanics. So just to summarize, so the projector onto the subspace in the direction of the unit vector n is this. And the projector in the opposite direction, opposite in 3D, then it's just this, right? Because I just replace n by minus n. And here, state n and minus n are orthogonal. So it's important to realize that states that are orthogonal in the Hilbert space are mapped into antipodal points on the sphere. Which sometimes when you do calculation, if you're not familiar, sometimes it can kind of confuse you, because orthogonal in Hilbert space, we usually think of it as 90 degrees apart, but here is 180 degrees apart. And by the way, if you want to write, if you're in 2 dimensions and you want to write a state that's orthogonal to some vector, then there's an easy trick, right? So this is just some trick. Yeah. So how would you write? If I give a state that's like alpha times 0 plus beta times 1, how would you write a state that is orthogonal to that? If you just have 2 dimensions. What do you mean? So by orthogonal, we know that this has to be true, right? Yeah. And then it's just a question of turning. Well, so if I write it like this, then it's just a question of turning the bra into the kid, right? Well, so the almost. Yeah, so if I flip this to the bra, then it will have alpha star and beta star here, right? But well, that would not make it orthogonal. Okay? Yeah. But in the case of in the case of the block sphere, you can write this explicitly in terms of the 2 angles too, right? So for the theta, obviously, if you flip the direction, just go to pi minus theta, and for the phi, I think it's the same as pi plus, I think. Right, so if I do it like this, right, theta would go to pi minus theta, right? Right, and then for phi, just add pi to it. Yeah, 4. And then you can also solve this equation to kind of invert this equation. Well, here you already know that identity is just diagonal in any orthogonal basis. But then I can also write this as by using those relations, n the projector onto n minus the projector onto minus n. And so this is a Hermitian operator with plus and minus 1 eigenvalues. And the plus 1 eigenvalues correspond to the direction, the n direction. The minus 1 eigenvalue corresponds to the minus n direction. And so you can use this as the traditional observable as well. It's just measurement of spins in the n direction. And so the outcome is just either your spin is in the direction n or the opposite direction minus n. So from this, actually, now you can easily calculate any eigenvalues and eigenvector of 2 by 2 matrices. Because I and the set of I and the Pauli matrix form an orthogonal basis for the operator space, which has dimension 4, right? It's 2 by 2 matrices. Well, how would you know this? Maybe it's kind of obvious there, even though here I just calculate, I just write a particular projector, right? Particular operators in terms of these 4 operators. But it is true that so how to argue that something is a basis, then you have to have the notion, a precise notion of vector space in mind first, right? And so here you can just naturally define the sum of linear operators, of 2 by 2 linear operators, and multiplication by complex scalars. And from there, you can argue or see that these 4 operators are linearly independent. But as you will do or you did in homework 2.1, you can also define inner product explicitly on this. You can define many kinds of inner products, right? But one of them is the Hilbert-Schmidt inner product. And this is that when I have an inner product of 2 operators, so this is Hilbert-Schmidt is defined to be this. And if you stares and thinks about it, then this is really just an inner product of 2 vectors that you obtain by, for example, like take each column of B and then just line up, stack them, stack each column of B into like a long vector, and then take the inner product of that vector with the same like stack vector from A. It's an inner product, really is inner product because you put a dagger here. Right, and so for example, it's well, you can show that this set is orthogonal according to this inner product, right? Because we already know the sort of algebraic properties of the Pauli matrices. So what are they? Well, if I square them, so any Pauli matrix, if I square them, I get the identity, right? And without calculating explicitly, well, so maybe I maybe I don't need to write this, but just write it for reference. If I write in the basis of Z, then it will have this form, right? And anyone who wants to work in quantum information would just memorize this. The only thing that you need to really remember is where to put the minus sign here, but that's the only thing. So all these algebraic rule you can derive by using like just multiply matrix in the matrix form, but you can also see, for example, this from this property too. That for all the Pauli matrices, so like for example, sigma x would just be sigma dot the unit vector in the x direction, right? And every one of them has eigenvalue plus, they're diagonalizable and has eigenvalue plus or minus 1, and so they square. When you square it, the eigenvalue just square too, right? And so you just get that identity operator. So maybe it's actually better to before that say that they are Hermitian. And well, you can write down the commutator and anti-commutator as well. But I can also write out the product first, and then the commutator and anti-commutator will follow. Oh, by the way, J and K here. So I'm not including the identity in here, right? There's just 3 Pauli matrices here. And this is, so if J and K are the same, it's just the identity, right? So you better have this. But then when you switch the order, you know that, for example, if I multiply sigma x and sigma y, I would get I times sigma z. But if I switch the order, like sigma y times sigma x, I will get minus I times sigma c. And so you will always get this I, but then the sign depends on the order, whether you multiply in the cyclic order or the opposite way around. And you have this Levi-Civita symbol here, the anti-symmetric, totally anti-symmetric symbol. And which implies basically this this part encode the right. This part encode the the commutator, right? And this is the anti-commutator. Maybe this is write down the properties of Pauli matrices. And the other property is that all the Pauli matrices has 0 trace. Okay, so with what we were talking about, so I was gonna talk about how this form a basis, right? And so suppose that I have this inner product, which like in reality you sort of have to prove that it's an inner product, right? Satisfy a property of inner product. But if I believe that this is an inner product, then if I can show that all the uh, all the operators in this set are orthogonal with respect to this inner product, then we are done, right? And we know that it is a basis, right? And in particular, an orthogonal basis. And so, for example, if I take an inner product of two Pauli operators, yeah, and the dagger here doesn't matter, right? Then what is the trace of this? How can you get from here? Yeah, so how would you do it? Yeah, and then what's the trace? Yeah, the second term is 0, right? So you only have things on this here. And since we are in 2 dimension, the trace of the identity is just the dimension just 2. So this is 2. Yeah. And so they are orthogonal, but they're not quite orthonormal, right? Because if you want to define orthonormal basis using this, then you have to divide everything by square root of 2. And of course, this because of the traceless, it's traceless. If you take the inner product of any Pauli operators with the identity operator, then you also get orthonormality too, orthogonality too. So therefore, from this relation, you can invert it to find. So suppose that I write a linear operator A in terms of coefficients A naught corresponding to the identity part, and then maybe just erase this first. So I just expanded this basis, right? Where here M doesn't have to be a unit vector anymore, right? And in fact, it can be complex too. That's okay. So to, oh well, why would I do this? Maybe I should have something that's related to A, like A, M or whatever. So now, since you know there are orthogonal bases, you can find this coefficient by just taking the trace of operator A with the Pauli operators, right? So the A alpha is 1/2 trace of sigma alpha with your operator A, where now I use the Greek index to refer to 4-dimensional vectors. Yeah, okay, so that's how you might in general find this expansion coefficient. For example, you can if you can do this to find the coefficient here of the projector, and then you should get the same result. Okay, so Thursday, yeah, we will continue this and talk more about operator space for qubits. Yeah, thank you. ปิดเรคคอร์ดไม่มีครับมีก็ได้แต่ผมสอนไม่ไหวผมต้องเตรียมสักครู่ครับสัปดาห์หน้าก็ไม่มีวันพุธเหมือนกันหรือเปล่าเพราะว่าผมก็ไม่อยากสอน3 วันต่อเหมือนกัน